All right. Okay, so actually first there's just a miscellaneous thing. All right. Back at the data directory, there is actually a data directory entry. So previously, so we're done with this now. We've X'd out the import directory thing. We already traversed all that path. There is actually a little helper thing here for the OS loader that's a pointer directly to the import address table. So if you want to go, you don't want to like traverse down. So the thing is, we saw before, if you have multiple modules which you're importing functions from, each of them points somewhere in the list, the overall list of imported addresses, right? So you don't, rather than having the OS go through and walk each of those and try to figure out where the import address table starts, there's this little helper thing where it can like just go directly to there if necessary. So this is just a miscellaneous point to check this off our list. So if you want to go directly to the import address table, the very start of the import address table, you can go to whatever index this is in the, whatever image directory entry IAT, whatever index that is in the data directory. That'll give you the RVA for the very beginning of the import address table. All right, so now we're going to talk about import address table hooking. So, right, when the import address table is fully resolved, it's basically just an array of function pointers in your module. So telnet.exe has an array of function pointers. You saw them. There were all those 777s. And there's probably some other ones before that, etc. Somewhere in the code path, there's like one of those call instructions where it says call, some offset in the table, pull that value out, and go to that address. So the problem is, what if the attacker is able to modify the import address table so that they take that value that's at that address, instead of being 77 whatever it was, what if it now points at the attacker's code? So in this case, what the attacker has functionally done is he's man-in-the-middling your calls to functions. So I've started to think about a lot of rootkit type things in terms of that it's really like a host-based man-in-the-middle. So on the network, you know that if the attacker is in between you and the server, right, they can do a lot of manipulations. They can, potentially break SSL sessions as long as they have legitimate credentials and stuff like that. A lot of the rootkit things that they do in order to hide stuff from someone, what it boils down to is that they've interposed themselves on something you'd want to ask about. You want to ask the operating system, is there this file there? What are the files in this directory? You ask the operating system, what are the files in the directory? The man in the middle says, oh, you want to know what files are in the directory? It's your operating system, tell me what files are in the directory. Comes back with a list, and it checks that list, and it says, oh, are any of those files my files? If so, remove those from the list, and then pass the query back. So import address table hooking is basically like, if instead of Bill over to the board, if instead of pointing to, actually, I think this is the example here. So we've got telnet.exe may call something in ntdll.dll. There's a kernel 32. I'm not sure which one it is in this thing, but let's say that, the user wanted to call some function in ntdll.dll, but instead the attacker came in and it took their modified their import address table. Let's say the attacker is here.
I'm sorry, Zeno. Can you adjust your microphone? You put your microphone.
Yep. Yep. I got you.
Thanks.
There we go. That should be better, maybe until I turn that way. How's this? Better? Can you hear? All right.
Sounds good.
So let's say the attacker is, somehow in the memory space of the thing he's trying to attack. And so telnet.exe, it used to have an import address table thing which pointed to ntdll. But the attacker comes in and he goes to telnet.exe and he says, no, that function is now going to point at me, and I'm going to eventually, call the ntdll that you originally asked for. And so by redirecting these function calls to the attacker, he's man-in-the-middling your function call, right? And so what we have here is we have a fun lab here where we're basically going to show how just using this user space sort of import address table hooking, we can actually hide a process, for instance, in a process list from Task Manager. Okay, now just to be very clear here, because this point comes up a bit. Again, every process is independent. The operating system is responsible We're taking user space processes and keeping them in separate memory spaces, right? If you're an attacker and you buffer overflow telnet.exe, right, that only says something about your ability to affect all of this stuff in this memory, right? That doesn't say anything about your ability to affect calc.exe. Now, you may have a method within Windows in order to like write memory over to some other process. And so there's ways which you can, you can subsequently jump from one process to the other process or into kernel and down to other processes and whatever else. But to be clear, how the attacker gets into the memory space is sort of immaterial for what we're talking about right now. We're just assuming somehow the attacker is in the memory space. They may be on the stack because they did a buffer overflow. They may be on the heap because they did buffer overflow. They may have just done DLL injection, which is what we're going to do, where they just somehow through configuring the system or calling function calls from some other thing to get in here, they just have some code running in this process address space. So once you assume that they're in the process address space and they can modify, the import address table of any of these things, but we'll say it's going after the main process, that's when this import address table hooking becomes a problem. So, like I said, it's sort of assumed, well, one way that you can assume that this is happening is through DLL injection. And so you can see this link for, which format got all messed up, but you can see the link for other ways that you can achieve DLL injection. We're going to do this the simple, easy, lazy way, which works good on XP and which is a little more effort on Vista, etc., but not really. So there is a registry key called appinit DLLs. With this registry key, basically, if you put the name of the path to a DLL in this registry key, it says that anytime anyone loads over to the board, anytime anyone loads user32.dll, every module that's currently listed in that appinit registry key will also be loaded into the memory space. So, and most everyone loads user32 because it has a lot of functions or it's depended upon by other things like NTDLL and stuff like that. So if user32 gets loaded into memory space, then any modules listed in this registry key also get loaded into memory space. So, if you're not monitoring changes to your registry and the attacker can somehow change the registry, then he'll be able to DLL inject. So what we did here is I modified this project right here. So this code project API hook one, it wasn't doing import address table hooking, but I just wanted to reuse some of its code. It was doing like inline hooking where, sorry, Bill, over to the board again. So here I said what we're going to do in our lab is we're going to go telnet, the import address table will get pointed to attacker, and that will go back to this. The alternate way is that you could change nothing in the import address table, right? And you could have something where, this still points there, but then that points to attacker, and then, and then attacker eventually points back to like there, and then that eventually returns to whoever called it. But the original that thing was inline hooking, where they basically took and put like jump instructions at the address of a particular function. So here we're hooking NT query system information. That's something in, where is it? Does it say there? I think it's in NTDLL. I think it's in NTDLL, but maybe it's kernel 32. So anyways, just lost my train of thought. So anyways, we're hooking this NT query system information. The original one would go directly to the first address of that, put a jump instruction which jumps to the attacker. Instead, we're going to modify the import address table. So I put the steps in here, and let's see if people can follow these along, just to see if your compilation environment is working or not, because we'll need it later as well. So what I need people to do is, if you grab the code from my home folder, in Life of Binaries, there's now a Life of Binaries folder, because it's double deep. And then you're looking for lifeofbinaries.sln. So this solution file, and when you double click that, you're going to open up in Visual Studio. And you should see something like this, more or less. So I have the original one here if you want to go look through it. It's more complicated actually than ours because he had to add in like libraries to disassemble the first instructions at the function he's trying to hook and stuff like that. So import address table hooking is actually quite a bit easier, but That one is much more generic. So that thing can hook anything. This can only hook things which are imported. So anyways, you've got import address app init hook IAT. Right-click on that and set that as startup project so that it becomes bold. All right, so now you can just go up and, I mean, you can, well, that's all right. I guess I'm going to go through the code just very quickly, just to show that this is an example where the attacker obviously has to know how the PE is structured in order to go find the import address table. If the attacker knows more than you, they win. All right, so basically, the basics, let's see. So we start with DLL main. I said that in DLLs, you optionally have this DLL main function, which is the first thing that's going to get called when it gets loaded into memory. So we know that in our circumstance that we're thinking about, we're just modifying a registry key so that this DLL will always get loaded into memory whenever someone loads user32.dll. So there's different reasons that this DLL main can be called. It can say like there's a new process just got loaded, there's a new thread that just got loaded, because the whole point of the DLL main is basically to put any code that needs to initialize, variables and stuff like that for the library. Put it in there so that if it sees a new thread got loaded, then it will initialize variables for that thread or whatever. So anyways, the main thing is this hook IAT entry for NT query system information. Mark, you missing something or no? Okay. Gotcha. All right, so I'm going to go to the definition of that. So you can right-click, go to definition, or just select from up here. All right, and this is the core aspect of, this is the core functionality of this malicious DLL. The first thing that it's going to do is it has this find this process address space. So it's like this DLL got loaded into somewhere. Over to the board, please. The DLL got loaded into some module, some address space. It doesn't know where it got loaded. It doesn't know what thing. It's just always going to get loaded for every new process that executes. The first thing it does is it consults this find this process base address is saying it's looking for whatever this main module is in this address space. It's looking for telnet, it's looking for calc, etc. And how it does that, I'm not going to dig into that. No, I'll dig into it because I really want me to. How it does it is the OS keeps some data structures. It basically keeps information like this in the linked list somewhere. So we saw before when we opened up WinDebug, it had all these addresses of all these locations, right? All the debugger was doing was just printing out some data structures in a linked list. For each module, there's this loaded modules list that says, telnet is the first thing that gets loaded. It's the first entry in the list. Then it goes, the OS goes to the imports. It says, oh, I see you need NTDLL. So that becomes the second thing. And then NTDLL, is user32, and that's the third thing. So every module in here is going to be in this loaded module list. And basically what the attacker code does is it goes to that list, and it says whatever the first thing in that list is, I think that's going to be the executable. It's just assuming at this point, right? It could do some sanity checking if it wants. But it basically is just assuming that because of the load ordering, because you double-click to this exe, that's going to be the first thing in the OS's list of loaded modules. So that's what this find this process base address does. And if we dig into here, we'll see some delightful assembly code, which I'm not entirely going to explain, but this basically, I'm not going to explain it at all, actually. Because you got a bunch of comments, and you can read those comments, which mostly just link you to this paper. So go read that paper. Actually, no, that's not even the main paper, because this is modified version, so oh well. The main thing is this is just saying it knows that this data structure will always be able to be found starting at, this FS register there. It goes to that, and it's basically just dereferencing its way through some structures until it finds the first thing. The only reason I went into this instead of just saying it is that code very similar to this is used for shellcode. So that when an attacker injects shellcode into a process, if they want to, for instance, find the address of some function they want to call like virtual protect or malloc or something like that, they can then go and search for something like kernel32.dll, which is a very useful module that has a bunch of things like changing memory protections, opening files, closing files. Kernel32 basically is the user space side of how you can call to a bunch of kernel space functions like opening files, closing files, stuff like that. So anyways, this little snippet of assembly code that I've written here, that's just, 5 instructions of inline assembly or whatever it is. This will basically go find the loaded module address list and then go immediately to the very first entry in that list. And so what this is going to return in this case for telnet.exe, the return value from this will be 01000000. It's going to give you the base address of the main process in the memory space wherever it got loaded. So what it does is it says exe base equals whatever that base address is returned by that. And then from there, it says, okay, I got the base address of a module. I'm going to parse my way through the data structures in order to find the import address table. And specifically, I'm looking for something, I'm looking for a specific entry, this NT query system information. And that's the one which it wants to replace with that function pointer. Instead, it wants it to point to its own function. And so this, yeah. So the long and the short of it is that, it sanity checks to make sure it can find the NTDLL. It then goes and finds the function pointer. And what this function pointer is being used for, what it's subverting in this case, is something like taskmanager.exe. When you call that and it gives you that list of loaded processes, running processes, right? So you see in task manager, here's, calc, and here's, explorer.exe. That list actually comes back. That's the return value from this NT query system information. So you pass them, you call NT query system information with a certain input, and the OS gives you back a list of all the loaded processes. So if the attacker So anyways, it's going around and it's basically looking, this while loop right here is basically just walking through the import address table, and it's saying, while this particular IAT entry, if that's ever equal to the function pointer address for the real the real NT query system information, if it's that, then I'm going to break out of my loop, and I know, okay, well, this IAT entry points at the address of the import address table entry, and then I'm just going to fill that in with my fake value after I change the memory permissions on the virtual memory, because the import address table is not writable after the OS writes it when it starts it up, but then it marks it as non-writable after that. So this attacker needs to mark it as writable and then change it. And so once he does that, the ultimate thing is just this assignment right here where it says, go to memory at this import address table thing and put in hooked NT query system information. And this is the modified one. And I haven't really looked through this, but just by skimming it, I can see, well, it's looking for calc.exe. And so I know that this code is actually going to hide calc.exe from the list of running processes. So what we're going to do is we're going to compile this DLL and then put it into the registry key and then see that taskmanager.exe is subverted. So you could right-click on appinit hook IAT and go to build. And you should get one succeeded. And then what we're going to do is we're going to go back out to our desktop where this life of binaries is. And under the debug folder, there will be a DLL now. So it should be like on your desktop, code, life of binaries, debug. And there should be a DLL. Appinit hook IAT.dll. So don't go into the project like at the highest level, right? So do not click into the folder called the appinit hook IAT. Just at the highest level, life of binaries where the .sln file is, go into debug at that level. And that's where you'll find the DLL. And so just for simplicity's sake, we're going to copy this to C:/, just so that the path is nice and easy. I'm going to copy that. I'm going to open up C:/. I'm going to paste that there. Just drag and drop it or paste it, whatever. So now, when you're done with this, you should have appinit hook IAT.dll in C:/. And then go ahead and open up regedit. So from start menu, run regedit.exe. And then in regedit, I'm going to go a bit slow here because this is, a bit deep. All right, from HKey local machine, and then software. HKey local machine, software, Microsoft. So HKey local machine, software, Microsoft. Then Windows NT. And current version. There's only one option under NT, current version. HKey local machine, software, Microsoft, Windows NT, current version, Windows. And then you'll see in that Windows folder the appinit_DLLs registry key. All right, so go ahead and put C:/appinit IAT hook or whatever it's called, .dll in there. So double click on the appinit DLLs, and then under value data, put C:/appinit hook IAT.dll. And now don't hit OK on that yet. So once you do that, once you hit OK, every new process that gets opened will have that being. But we want to be very clear on that this change has actually happened. So before we set this registry key, right, let's run calc.exe. Right, so we run calc.exe, and we run task manager by either hitting Control-Alt-Delete and selecting task manager, or by just going to run task manager. I'm having troubles here. Oh, wow. Awesome. Off to the side. Come on. Come on. Come on. There we go. Kind of. So under Task Manager, under Processes. Now this is specifically sort the processes by image name, and you'll see calc.exe. Only this list is what is coming back from NT query system information. And we'll see that when we hack this, calc.exe will disappear from here, but it won't disappear from applications because this list is not what it's coming back from. This is from somewhere else. So just the process list will be having this executable hidden. But of course, you know that there's plenty of processes in here that are not showing up under applications. So it's not as if you can't just make your process non-visible. So anyways, Task Manager, you should be in Processes tab. You should have it sorted by name. You should see calc.exe. Assuming you have calc.exe open. All right, so now we're going to close this, and we're going to hit OK on that registry change. And once we do that, the next time that we open Task Manager, so run Task Manager, task mgr. The next time we run Task Manager, calc.exe doesn't show up here because, right, it's a rootkit. This is a non-weaponized rootkit. This is what user space rootkits are, and we'll get into this a bit more when we have the rootkits class. But yeah, so the whole point is this list just comes back from this single function, right? And so all the rootkit has to, well, all this malware has to do is interpose itself on your call to that function. You say, give me the list of processes. It takes that and says, okay, they're looking for the list of processes. I'll go ask the operating system. I'll check the list when it comes back. And if I see calc.exe, I will remove it from the list, and then I'll pass it back to the user, right? And so if we want to see this actually, really see the change where it's actually happening, we can then go ahead and open WinDebug, and we can go look at the import address table. So I'm going to close Task Manager. I'm going to open WinDebug, but WinDebug is actually going to get hooked as well, but that's okay. Oh wait, no, that's not okay because then I can't open it in WinDebug. Yes, good. Let's show that. All right, so I'm going to go to All Programs, Debugging Tools, WinDebug, and I'm going, oh, I know what I wanted to do. Yeah, oh well. Okay, I'm just going to run Task Manager first. All right, so I've got Task Manager running. Task Manager can't see calc.exe. I've got WinDebug running, and now I want to take WinDebug and I want to attach to the running Task Manager. It's already running, it's already hooked. So I'm going to attach to Task Manager. But, oh good, it is there. Never mind then. Yeah, so it can actually attach. So for some reason I was thinking it was like, it was being hooked as well and couldn't see it, but it could be. There we go. So first of all,
What exactly did you attach to the task?
I attached the debugger. So basically, OSs are, for debugging purposes, the OS is going to export some API where it can say, like, debuggers can attach, they can read memory, they can maybe write memory, and stuff like that. So the point is, WinDebug is using the OS API to say, dear API, let me, attach to this process. So the first thing I can see here is that, oh, right, I can't move that anymore because it stopped. That's going to be inconvenient in a second.
Oh, I see. 'Cause I had it.
Right. I'm going to make this small. Okay, it doesn't want to go any smaller. I'll make it small horizontally then. I run WinDebug, I go attach to a process, I go select taskmanager.exe, attach to it, and so first of all we can see the appinit hook iat.dll loaded into its address space, right? This is what enables the code to go in, change the import address table, and redirect it over to their code. And so this, in and of itself, one could think, one possible remediation for things like DLL injection is to profile executables and understand, what possible processes are within their loaded memory space. But that can get quite complicated. So the other thing we can do is we can go in and we can say, let's go look at its import address table and see, does it look like it's even pointing into the right module, for instance. That's one heuristic. Let's see, what am I going to do? I'm going to open up Task Manager in PEView so that I can cheat and go find the import address table for the NT query system information. So, Task Manager is actually, just in C:\Windows System 32 like the other things were. So C:\Windows System 32. I can open that in PEView. I can, cheat and go find the import address table directly. I can be annoyed by the fact that Task Manager is in my way. And then I can scroll down to ntdll.dll, right? So actually, the nice thing here is that PEView, right, this last entry, this is just 000, that's just terminating this thing. But PEView is being nice and it's saying, hey, all of this array above that 000, these were all the functions imported from ADV API 32. These are all the functions imported from COM-CTL 32, etc. So I can just keep scrolling down until I find ntdll.dll. I think that's it. Oh, it's 32. There we go. Looks like it's at the very bottom. Right, so within this, I'm looking for this one right there, NT query system information. So this is the thing in the import address table. It's saying, well, I'm going to change this to RVA view up here. Change that to RVA view, and it's saying at RVA 1448 into taskmanager.exe, that's the import address table entry for NT query system information. And so if I go and look at my process that I've attached to at offset 1448, right? So Windebug is telling me task manager is at base address 10000, same as telnet. Copy that. I'm going to make a memory window again. Split the top of my screen. Put in the base address plus 1448.